guys, how's it going today? Today we're going to start looking at radiation. Our goals for today are to first explain what radioactivity is and why it occurs. We will then look at three major types of radioactive decay: alpha decay, beta decay, and gamma radiation. For each of these, we will be describing both the radioactive particle that is released and the overall effect it has on the decaying radioisotope. In order to understand radiation, we first have to talk a bit about nuclear stability. The nucleus of an atom can often be unstable, usually due in large part to the ratio of neutrons to protons within the nucleus. In general, smaller elements have a stable nuclei when the ratio of neutrons to protons is close to 1. Carbon-12, nitrogen-14, and oxygen-16 are all common examples of stable isotopes with a 1-to-1 ratio. Larger elements, on the other hand, tend to need more neutrons to be stable. For example, while a stable helium isotope might have 2 protons and 2 neutrons, a stable isotope of lead has 82 protons and 126 neutrons. Of the approximately 1,500 known atomic nuclei that scientists have discovered, either naturally or in the lab, only 264 of those are stable. So what happens when a nucleus is unstable? When a nucleus is unstable, it releases energy and particles in order to reach a more stable state. This is referred to as radioactive decay. Elements that are prone to radioactive decay are often referred to as radioactive elements or radioisotopes. The nuclei of radioisotopes lose energy by emitting radiation, which comes in three major forms: alpha radiation, beta radiation, and gamma radiation. Radioactive decay is an interesting process, as it is one of the few processes that can change an atom from one element into another element, and one of the only times in chemistry where mass is not entirely conserved. During radioactive decay, an incredibly small amount of mass can be turned into energy, though only during specific types of decay. Let's take a look at the major forms of radioactive decay, starting with alpha decay. Alpha radiation occurs when a radioactive nucleus emits an alpha particle, which is effectively a helium atom. It has 2 protons and 2 neutrons, and is by far the largest form of radiation, which is both good and bad. It can do a lot of damage to soft tissues and cells, but it has a tough time penetrating deep enough to actually do this damage. Alpha particles can be stopped by something as simple as a piece of paper, so they really only do their major damage when they are ingested. Let's take a little deeper look at how alpha radiation reactions look. So before we get started, we're first going to need to talk about this new type of notation we've got. Up here you can see that you've got this uranium with a 238 and a 92 to the left. The 238 is the mass number. Remember that the mass number is the number of protons plus the number of neutrons. The number at the bottom is the atomic number. So this is just the number of protons, which means from here, you should be able to determine that there are 92 protons, and since you have 238 when you add the number of protons and neutrons together, you've got 146 neutrons in this uranium atom. We write these out as uranium-238. This dash tells us the mass number right here. And this is just because uranium will have a bunch of different isotopes that are all radioactive. Uranium-235 is another really common example of a radioactive isotope of uranium. Now, we've got our sort of decay symbol. This is the same arrow that we would use in normal chemical reactions, but it is just a decay reaction. And then this one, we've got the same thing. So we've got our mass number, we've got our atomic number. The element now is thorium, because you'll notice that the atomic number went from 92 to 90. And of course, the atomic number is what determines what type of element this is. So 90 is thorium. You can check on your periodic table if you want to. And then we added this alpha particle. This alpha particle has an atomic or a mass number of 4 and an atomic number of 2, because there are 2 protons and then there are 2 neutrons, resulting in a mass number of 4. Occasionally, you'll see that alpha particles are also written as 4,2 alpha or just alpha. I'm always going to write them as HE just because it's a little bit simpler, but they can be written with the alpha symbol instead. Now, you'll notice that this results in a different element being formed from the original, thorium from uranium, that has an atomic number that is 2 less than the original and a mass number that is 4 lower than the original. So basically, whenever we have alpha decay, we're always going to have a product result in an alpha particle, and an element that has a mass number, the top number, is going to be 4 less than it was before, and the atomic number, the bottom number, is going to be 2 less than it had before. So this question asks us, what are the resulting products of the alpha decay of thorium-230? So first things first, we can write out our thorium-230 here. Thorium-230. And from up here, we know that thorium is a 90. And that is going to decay to something here and our alpha particle, 4, 2, helium. Now, the way we can solve this is we know that whatever the product is going to be 230 minus 4. So that's going to be 226 at the top, and then 90 minus 2, or 88 at the bottom. And then all we have to do is look up what element 88 is on our periodic table. And in this case, that happens to be radium. So there we go. That's the resulting product of the decay, alpha decay of thorium-230. Now let's look at beta decay, our second type of radiation. Beta radiation occurs when a neutron actually splits into an electron and a proton. The electron is emitted and is the beta particle, but the proton remains in the nucleus. Beta particles are significantly smaller than alpha particles, being composed of only a single electron, rather than 2 protons and 2 neutrons. This means that they aren't going to do as much damage to whatever they hit, but they can penetrate far better than alpha particles. Luckily, beta particles can still be stopped by aluminum foil or a thin piece of wood. Now let's look at the reactions for beta decay. So up at the top, we've got 146C. Remember, this is our mass number and this is our atomic number. So we've got carbon 14, which is decaying to nitrogen 14 plus a beta particle, which is just an electron with a 0 and a minus 1. Now, the reason that this is going from 6 up to 7 is not because an electron does not contain a negative proton. But when the beta decay happens, a neutron, which is effectively just adding up to this top number, splits into a proton and an electron. So during that initial split, you gain 1 proton and you gain 1 electron. The electron gets emitted, but you've still gained 1 proton overall. So what you're going to have is during beta decay, you're going to have a +1 to your mass or your atomic number, and your mass number is going to stay the same. That's why we write this electron as a 0 and a -1 in the protons. Again, the electron itself is not a negative proton, but it effectively adds 1 proton to our atom here. So we write the -1 at the bottom. So this question here asks us, what are the resulting products of the beta decay of thorium-234? So we'll start with this, thorium-234. Thorium is element number 90. And that is going to decay to something plus our beta particle, 0 minus 1 E. And in this case, remember our mass number doesn't get changed, so 234. And our atomic number is going to go up by 1, so 91. So all you have to do is look up what the 91st element is, and that is protactinium, I think. I'm not 100% sure how to pronounce it, but it's Pa. The last form of radiation we'll talk about is gamma radiation. Gamma radiation is effectively just electromagnetic radiation, like UV rays, X-rays, or light. Gamma radiation is, however, very high energy or electromagnetic radiation. So high energy, in fact, that it can be very dangerous. Gamma radiation comes in the form of gamma rays, and these rays are usually emitted alongside alpha particles or beta particles. Since gamma radiation is really just a release of energy, they don't result in much of a change for the decaying nucleus. They are, however, possibly the most dangerous form of radiation, as they are very difficult to stop. Gamma rays can be stopped by concrete if it is several meters thick, or by a few centimeters of lead. So before we finish up today, we're going to look at a couple practice questions. And all we're trying to do in these questions is determine whether the following reactions are examples of alpha or beta decay. Now, I would strongly encourage you to go ahead and try these on your own, because if you've been paying attention, hopefully you can figure out how to do this already. But I'm going to go ahead and talk about it in just a couple seconds. So pause if you're going to need a little bit more time to do this. Basically, in order to solve these equations, we actually don't have to concern ourselves with anything on this side. All we're going to be doing is looking at the particle that's being released. All we have to do is determine whether it's an alpha particle or a beta particle. And we know that alpha particles are these 4,2He's, which is effectively just a helium atom. So we know that this is alpha decay, because this is our alpha particle right here. Label it with an alpha. And then this one, which is the electron, this is our beta particle. And so we know that this must be beta decay. So this is going to be beta as well, and this is going to be alpha as well. And that's all you have to do if you're determining whether or not a reaction is an example of alpha or beta decay. Gamma radiation can be written alongside any of these as the gamma symbol, which I believe looks like that, though I'm not 100% sure. But again, since that doesn't actually change the nucleus, there's not a whole lot of point in writing it out in most of these. Let's review. Unstable isotopes of elements are called radioactive and are referred to as radioisotopes. Radioactive nuclei decay radioactively by emitting energy from their nucleus, and these emissions come in three major forms: alpha radiation, beta radiation, and gamma radiation. Alpha radiation, or alpha decay, involves the release of a helium atom, and results in a new isotope with a mass number 4 lower than the original and an atomic number 2 lower than the original. Beta decay involves the breakdown of a neutron, which forms a proton and an electron. The electron is released as a beta particle, and the resulting isotope has the same mass number, but an atomic number 1 higher than the original atom. Gamma radiation just involves the release of gamma rays, which are a form of electromagnetic energy. Basically, gamma radiation is a release of energy that usually occurs alongside alpha or beta radiation. That's it for this video. Thanks for watching, and I'll see you next time.